The following is part of a college course based on the textbook Horizons, Exploring the Universe, written by Michael Seeds and published by Thomson Brooks Cole Publishers.
Not the least obeisance made he, not a minute stopped or stayed he, but with mien of lord or lady perched above my chamber door.
What does astronomy have to do with a man standing in a forest, eating raisin bread, and reading a poem? All of these things are related by the field of cosmology, the study of the origin, nature, and evolution of the universe. The trees in the forest are the stars filling the sky. The raisin bread is the universe itself. And the poem? That's by Edgar Allan Poe. And while deep into the darkness peering, he became the first person to suggest that the universe had a definite beginning. Why is the sky dark at night? This seemingly simple question has been asked for centuries, but it was popularized in 1826 by a man named Wilhelm Olbers, so we now call it Olbers Paradox.
Well, Olbers Paradox is a very old and easily understood problem or thought experiment, if you like. And if you imagine an infinite universe, one that goes on forever and has no spatial boundary or end, then if you look out at the night sky, it is inevitable that any line of sight that you take is eventually going to come to the surface of a star, whether it's in our galaxy or somebody else's.
Like the man sitting in the forest, who sees trees no matter in what direction he looks, an infinite and eternal universe implies we should see stars wherever we look. If stars uniformly filled the sky, then every spot on the sky should be as bright as the surface of a star. But the sky gets dark at night.
And so Olbers' paradox was, that isn't what we see. When we look up into the sky is mostly dark with just a few stars in between. So what's the resolution to Olbers' paradox? Well, the first, which would be very obvious, is that the universe is not infinite, that ends somewhere. Okay. Another way that you can solve Olbers' paradox is if, as you go farther from the Earth or wherever you're looking from, the universe changes its character in some way. It's not Euclidean. A third way to solve Olbers' paradox is to say not that it's finite in extent, but it's finite in time. It had a certain age. And because it has a certain age, you can only look out to a distance which is equal to the age of the universe in light years.
The best answer to Olbers' paradox is the last of these three choices. The universe must have had a beginning. In 1848, Edgar Allan Poe wrote Eureka, a prose poem, a work in which he tried to deal with many of the issues of astronomy and the beliefs of his day, including Olbers' paradox. In this work, he suggested that the universe is not infinitely old, and the light from distant stars had not yet reached the Earth. He established the concept of an observable universe, the portion of the universe that we can see, but which may only be a part of a much larger and possibly infinite universe. Poe had leaped from the accepted idea of the day that the universe was eternally old to the concept of a universe that had a definite beginning. His foresight was 2020. Although imaginative and in many ways correct, Poe's work was not scientific, and it would take observations in the early 20th century to begin building the model he postulated in his work. The model of the universe at the beginning of the 1900s was static, unchanging in size. In 1916, Einstein reinforced this concept of a static universe in his general theory of relativity.
Einstein was led by a philosophical or almost theological feeling that the universe has always been the same and always will be the same. It's static. That is, the distance between the galaxies doesn't change, that the universe is infinite backwards in time and forwards in time, that we're in the middle of something that is an infinite process. And so when he created his equations of general relativity, he immediately saw that they were not stable. That is, all the galaxies felt each other, they felt the gravitation, and the gravitation is attractive, and so all the galaxies will start collapsing into each other. And so in order to counteract that, he put in the only term into his equations that would maintain the symmetry of the equations, and that term is called the cosmological constant. It added just enough to make the universe static. That is, he added just enough to keep all the galaxies just from starting to attract each other and collapse.
Around that same time, in 1929, Edwin Hubble published results based on his work and others, which would prompt Einstein to say that adding the cosmological constant to his equations was the biggest blunder he had ever made.
Edwin Hubble, around 1930-ish, made the observation that galaxies that are fainter, apparently farther away, have spectra that are Doppler shifted to the red in the spectrum, red shifted, in increasing amounts as they are farther away or as they are dimmer. So there was a relationship then between, for example, the brightness of a galaxy and the Doppler shifting, the red shifting of its spectrum. That has been substantiated over time. We see it very clearly now.
What Hubble and others had discovered is that the universe is expanding. This doesn't mean the galaxies are moving through space away from our location, but that space itself is enlarging and carrying every galaxy away from every other galaxy. This is where the raisin bread comes into the picture. We can picture the universe as a loaf of raisin bread dough baking in an oven.
And you can think of the galaxies as individual raisins within this bread. So you can imagine this raisin bread is expanding. And as it expands, the raisins get carried along, which is what's happening in the universe too. The space is expanding, and as space expands, it's carrying all these galaxies along with them. So you can imagine two raisins that start off really close together in this raisin bread. As the raisin bread expands, they're going to move apart a little. But take two raisins that are on opposite ends of the raisin bread, and as the raisin bread expands, those move apart even faster. And it turns out, if you work it out, the further apart the raisins are, the faster they'll be moving away from each other.
This uniform expansion was observed by Hubble and other astronomers, and it meant that the universe had a beginning.
Well, this whole model of the universe expanding is based on the fact that when we look in a certain direction, we see galaxies, and they all appear to be moving away from us. Okay, and then we look in another direction, they all still appear to be moving away from us. Now, our simple-minded idea is, if they're moving away from us, then they are further away from us today than they were yesterday. And yesterday they were a little closer, and the day before they were a little closer, and the day before they were a little closer. And you come to a final conclusion that all of those galaxies were all in one spot at the beginning.
But unlike the loaf of raisin bread, the universe has no edge and therefore can have no center. Because it is difficult for us to conceive of an infinite universe with no edge or center, it helps to make an analogy with the surface of the Earth.
We could start walking from one spot on the Earth, and we could walk all the way around the Earth, never ever hitting an edge, and in fact coming right back to where we were to begin with. Okay, so we'd never hit an edge, we'd never hit the center, and now imagine that the Earth is expanding. So now we start walking in one direction, and the Earth keeps expanding, and we keep walking. And if the expansion is fast enough so that no matter how fast we walk, we never ever really get around back to where we started. There's no edge, there's no center. It doesn't make sense to talk about the edge of the surface. There is none, right? It's all, and that's the way to think about the universe in general.
Because the universe is expanding, it had to be smaller in the past. It had a beginning. So everything in it was at one time compressed in a hotter, denser state. At the very beginning, what some scientists call time zero, all of space, time, energy, and matter were combined and at that moment were created as separate entities. That event, called the Big Bang, was the moment when everything we know came into being. The Big Bang was not an explosion in space, it was an explosion of space, as well as energy, matter, and time itself. It filled the entire universe because it was the entire universe. And as the universe expanded, this tremendously hot soup of energy and matter cooled and became less dense. Eventually, it would condense to form the stars and galaxies that would lead to the formation of planets and us. But while it was still hot, it emitted visible light, and today we can detect that light, though it is now highly redshifted. But its discovery was a surprise. In 1948, George Gamow predicted that a hot Big Bang would emit large amounts of radiation. A year later, Ralph Alpher and Robert Herman estimated that the expansion of the universe would have shifted this radiation to the far infrared and radio end of the spectrum. These predictions were followed by assertions in 1964 by Robert Dickey at Princeton that the newly developed radio telescopes should be able to detect this radiation. Coincidentally, around that same time at Bell Labs in New Jersey, two engineers named Arno Penzias and Robert Wilson were working with a giant collecting horn designed to focus energy from the microwave portion of the spectrum into sensitive detectors. But they were being plagued by a pervasive hiss which interfered with their work. Penzias and Wilson thought the hiss was related to their instruments, but when they investigated it, they made the discovery of a lifetime.
They thought it might be something with the instruments. So there's stories about them going up and cleaning off, bird poop and stuff from the horn itself, but they couldn't get rid of it. Everywhere they looked, they kept seeing this radiation. They had no idea what it was due to.
When a coworker happened to mention Dickey and his predictions about the detectability of the leftover radiation from the Big Bang, Penzias and Wilson realized that the hiss in their receiver was precisely this: cosmic microwave background radiation, the highly redshifted light from the original hot gas filling the universe. The hiss was direct evidence of the Big Bang.
The cosmic background radiation is the Big Bang, and we see it in all directions. You look in every direction in the sky and you see this radiation, and that's the glow of the Big Bang. It's all around us because we were part of it and we're inside it. And when we look out to great distances, we look back in time and we can see that Big Bang wall of fire way out there.
The discovery of cosmic background radiation triggered a revolution in cosmology. Cosmologists began to focus on how this all happened by studying the background radiation. By doing so, they could find a wealth of information about the universe. One of the most critical was its age, 13.7 billion years. The background radiation was formed 380,000 years after the birth of the universe, and the first stars 200 million years after that.
Let me talk a little bit about our current theory for how the universe evolved from the Big Bang. But within the first 3 minutes, what happened was all of the matter, all of the ordinary matter of the universe was created, essentially condensed out of a high-energy soup. And as the universe cooled in the first 3 minutes, electrons, protons, and neutrons were created out of this soup. And then as it expanded and cooled through the first 3 minutes, eventually the protons and neutrons began to get together into nuclei. Then over the course of the first 100,000 years, they evolved to the point where the electrons and the protons and neutrons captured into atoms. So they created a neutral atoms, and a neutral universe followed right after that. From about the time of 100,000 years after the Big Bang until 100 million years, we don't believe very much was going on. At least right now we think of this as a great period of the Dark Ages, where there were no stars, there were no galaxies, nothing that shined.
This dark age set the stage for the formation of stars and galaxies and even larger structures. The process was not perfectly smooth, with matter and energy evenly distributed throughout the universe. Instead, It was just a bit lumpy, rippled ever so slightly.
Well, COBE, the Cosmic Background Explorer satellite, and its very capable successor, the Wilkinson Microwave Anisotropy Probe, were wonderful scientific instruments that looked like a brass band. They had feed horns that record microwaves. So as they look around us in the universe, they see this bath of microwave radiation that is the remnant fireball in which we were immersed in the moment of the Big Bang and remain immersed as the universe expands. And that the little ripples in that are the remnants of the sound waves that were propagating through the mass energy in those early days, and those ripples tell us about how the structure that ultimately became galaxies and clusters of galaxies was seeded.
The gravity within those ripples began to act to collapse them, and as they collapsed, they eventually compressed the matter so much that they turned into stars. And when the stars began to shine, it put radiation back out into the universe. There was a point at which the radiation was enough to reionize the universe, that is, to strip all the electrons from the protons again. And then a period from about 1 billion years or 2 billion years out to about, say, 3 or 4 billion years was a period of rapid buildup of galaxies.
Galaxies clustered into great walls and filaments separated by voids to form the large-scale structure of the universe. The distribution of these structures in the universe can be linked back to the ripples seen in the cosmic background radiation,
called the cosmic microwave background radiation. Now, it's very smooth, meaning that the universe is very uniform everywhere. All points are pretty much typical. But there are some fluctuations in it, and those are associated with the fact that there had to be some inhomogeneities in the distribution of matter in the early universe, because galaxies and clusters of galaxies formed through the gravitational contraction of the slightly overdense regions, and then the voids between clusters of galaxies formed in the underdense regions. Well, the denser regions had a slightly different temperature than the underdense regions, and we can see those tiny variations now with very precise measurements using radio telescopes. We can calculate what the typical size, the physical size of the fluctuations was at the time that the microwave background radiation was set free, about 380,000 years after the Big Bang. And by comparing the known or calculated physical size with the observed angular size of these fluctuations, we can tell the geometry of the universe.
The concept of the universe having a geometry is difficult to grasp. The geometry actually refers to the curved path followed by light under the pull of gravity. Einstein first postulated that space behaves like a fabric in which matter is embedded. The gravity of matter bends space locally, but space can be bent on a cosmic scale as well. And it's this warping that's called the geometry of the universe. The geometry can be determined by measuring how rays of light propagate through space, and, once known, astronomers can then uncover the relationship between the universe's composition, age, and final fate.
You get one relationship if they travel along Euclidean straight lines. You get a different relationship if they travel along a curve, like on the surface of a beach ball, and yet a different relation still if they travel along like a horse's saddle or a potato chip.
The model of the beach ball describes a closed universe where there is enough matter and gravity to force light to travel on closed, curved paths. It used to be thought that a closed universe would ultimately slow its expansion due to gravity, and then recollapse on itself. This now outdated model is sometimes referred to as the Big Crunch. The potato chip, or saddle model, is an open universe where light rays diverge. In between the open and closed models is a universe with no curvature, so it's called a flat universe. Light rays in a flat universe that start out parallel will remain parallel. To determine the correct model, astronomers had to quantify the average amount of mass and energy in the universe so they could calculate the resulting gravity and determine how strongly it would curve light. The most precise way to determine the density of mass and energy in the universe was by carefully observing the fluctuations in the cosmic background radiation.
What the radio astronomers found was that the observed angular size of these fluctuations corresponds to a universe in which light travels along Euclidean straight lines.
This meant that the geometry of the universe was flat.
But according to Einstein's general theory of relativity, for light to do that requires the average energy density of the universe, the energy per unit volume, to be some considerable amount, okay? It's got to be a fair amount of stuff out there to cause the universe to be flat. What we observe to be out there in terms of visible matter and the inferred dark matter that binds clusters of galaxies is only 30% of what is needed to make space geometrically flat. So the other 70% has to be something else. It cannot be gravitating matter, because we know about all that. Well, it could be this anti-gravitating dark energy.
Dark energy is theorized to be energy that fills empty space and drives the expansion and flatness of the universe. Its form is not yet certain, and its exact properties are not understood. The best way to study dark energy and its effects on the universe is to observe the universe on the largest of scales and to find some standard beacon that can act as a benchmark. Astronomers found that beacon in a certain kind of exploding star called a Type 1 supernova.
By looking at how quickly a supernova brightens and fades, we can tell its intrinsic peak power. So you measure the light curve, the brightening and the fading. If it's slow, that's a luminous one. If it's fast, that's a subluminous one. If it's average, then that's the normal one in the assumed power of the supernova. And that really improves their utility for cosmological distance measurements, makes them really superb.
And so when we saw these things happening at large distances, we knew how far away they were. And what was proving to be the case was that these very, very distant supernovae were fainter than we expected.
And that's what shocked us. When we measured this, we expected the galaxies to be much closer to each other, but they were actually farther apart. They were farther apart by about 12% than what we expected. Something was pushing them, just like if I throw this ball up in the air, the ball will go up a certain distance and come back. But something, since the galaxies were farther away, something was actually pushing that ball, something was pushing that galaxy farther and farther away. It was pushing against gravity.
That something is proposed to be dark energy, invisible yet filling space, exerting an outward pressure which accelerates the expansion of the universe.
So this weird stuff that's pushing the universe apart faster and faster, it kind of like has anti-gravity. Now, we don't like to put it that way because it's not dependent, we think, on the masses of anything. We think instead that it's a property of space. From the observations, we can tell that it's got about the same amount per unit volume. It's got about the same density everywhere in space. And even as space expands and the universe becomes bigger and more dilute, the amount of this stuff per unit volume, its density, apparently is remaining the same or nearly the same. Now that's really weird. You know, if I have a box with 1,000 particles in it and I expand the box, the number of particles in the box stayed the same, and so the number of particles per unit volume decreased. But in this case, this weird stuff that's pushing the universe apart has a constant or a nearly constant density. And that means that as the universe expands more and more, there's more and more of this stuff between the galaxies, and so its cumulative effect increases.
This acceleration of the expansion of the universe was a total surprise to astronomers who always assumed the expansion was slowing. This opened a whole new arena in cosmology and raised many more questions than it answered.
The universe is a battle of the dark side, a battle of the dark matter and the dark energy. So the dark matter is tried and successfully built up a universe, and the dark energy is pushing it apart. And right now, the dark energy is winning the battle. Will it continue to win the battle? What's the future? So is the dark energy going to win the future and things get farther and farther apart and fewer galaxies to see? In terms of the dark matter question, we know enough now to say that the dark matter is not made out of atoms. It's not made out of the stuff that you and I are made out of. The dark matter, we believe, is made out of a new form of matter, a new kind of elementary particle. And so the adventure has gotten even more interesting because it's not just astronomers who want to know what the dark matter is. It's also physicists who are trying to understand the micro world and how the world is put together at the smallest distances. And so this dark side has become a very important area, not just in astronomy, but in physics.
Amazingly, what started as an attempt to understand the very largest of cosmic scales has brought us into the realm of the very smallest, the subatomic. The properties of dark matter and dark energy may ultimately be found not by searching the farthest reaches of the universe, but instead by performing particle experiments with supercolliders here on Earth. This may even lead to the formation of a grand unified theory that will marry the physics of the large, written by Newton and Einstein, with the physics of the small, known as quantum mechanics. By doing so, we'll have gone full circle from our human view through the infinite down to the infinitesimal and back again. The history of science and of humankind is full of journeys that started with a small step. But one of the grandest may have started by merely looking up. Wilhelm Olbers asked why the sky is dark at night, and Edgar Allan Poe's simple reply was that the universe had a beginning. And now, when the sophisticated tools of modern science are brought to bear, we find that Poe's work is not destined to be a quaint and curious volume of forgotten lore. He helped spur what would become the scientific field of modern cosmology. Perhaps Poe would have been delighted with what we have learned since his pondering. He may have enjoyed knowing that the fate of the universe can now be determined. It will expand eternally, ever growing, ever faster, forevermore.